Good afternoon and welcome to this webinar hosted by Element 14 in association with Vishay Precision Group. Today we'll be talking about Vishay for resistors in lithium-ion and alternative energy applications. Today we have with us Kevin Smith, Richard Zurat, and Victor Chertakowski of Vishay Precision Group. If you have any questions for the panel during the course of the webinar, please put them either into the chat or the Q&A window, and I'll ask them of the panel at the end. Without further ado, I hand you over to Kevin Smith. Take it away.
Thank you very much, Christian, and welcome everyone to this Vishay Precision Group, Vishay foil resistor presentation on lithium-ion and alternative energy applications. First of all, a few words about our company. Our company is Vishay Precision Group, and we were formed as a spin-off in 2010 from Vishay into Technology. We have recently changed our logo and our company branding to VPG to differentiate us from Vishay into Technology, and our website is now www.vpgsensors.com. You can also reach us at www.vishayfoilresistors.com, which is still the brand name of our products. And as the name suggests, we manufacture precision bulk metal foil resistors, which we will explain in detail during this presentation. Okay, so let's get straight into the subject at hand. So, here we see the charging method for a lithium-ion battery. And there are two curves on this chart. And what this shows is that there are two distinct phases to correctly charging a lithium-ion battery. You start with the constant current phase, and you switch to a constant voltage phase. If you look on the diagram at the line where it says cell voltage, this is the constant current phase during which the current is maintained at a constant level and the cell voltage rises. Once the cell voltage reaches a fixed level, 4.2 volts, you then switch to the constant voltage charging domain, and you maintain the charging voltage at 4.2 volts, and the charging current will then reduce to a defined level at which you then stop charging. And at this point, the cell will be fully charged. So just to reiterate, in order to correctly charge a lithium-ion battery, there are two distinct phases required as constant current, switching to constant voltage. And both of these phases require precise and accurate control of current and obviously voltage. One point here to clarify, in this presentation and in battery literature in general, it's often referred to as C, a parameter called C, and C is normally defined as the cell capacity in amp hours for a particular battery. So if, in this example, we have a 1 amp hour battery, then the current for the constant current phase at 1C would be 1 amp. And we'll come on to that in a little bit more detail in a moment.
Kevin, this is Rich. This graph, this charging graph sums up today's topic very, very nicely. All very, very complete right here.
Okay, so a few points in a little bit more detail about the charging of lithium-ion batteries. As I said, first of all, the cell capacity is the amount of charge that can be stored, and is generally expressed in milliamp hours. As I already said, charging starts with a constant current phase, and this would vary by the manufacturer of the battery, and it will be specified in the data sheet, but it's normally in the range of 0.2C up to 1C. In which case, the value of the current is equal to the capacity. So again, if we had a 1 amp hour battery, 0.2C would mean 0.2 amps of charge current. Very importantly, once the battery reaches 4.2 volts, plus or minus 50 millivolts, and that's volts per cell, the battery must then be held at this voltage until the termination condition is reached. And this again will be defined by the battery manufacturer, and it will typically occur when the charging current has then dropped to 10% of the initial charging rate. For safety, we will cover safety later on, but a maximum length of charge timer is normally included to prevent the battery from being charged for too long, and also the battery temperature should be monitored. One question that's frequently asked is, well, can we not just charge to 4.2 volts and then stop charging? What will happen if we do that? Well, you can do that, obviously, but the problem is that if you do that, you will only get between 40 and 70% of the maximum capacity of the battery, unless you're going to charge it very slowly. So if you want to have full capacity, you do need to continue charging until the current drops and the termination condition is reached. And finally, a note of caution, lithium battery ions must not be overcharged. As we've all seen from a lot of press coverage, and I think it's well known in the industry that certainly if you overcharge lithium-ion batteries, by which I mean charging above 4.3 volts per cell, this causes chemical reactions inside the cell which increase the pressure and if allowed to continue will cause a catastrophic failure of the battery.
Just to quickly add, charging any battery can be potentially hazardous, even your car battery. But if you follow along with the webinar, you'll see why a lithium-ion battery is especially so.
Okay, so some quick Q&A points on charging. So what happens if the charge voltage is less than 4.2 volts? Well, basically, the battery will still charge, but it will never reach the full charge. The chemistry of a lithium-ion battery means that you need to reach the 4.2 volts in order to achieve the maximum capacity. And here's the explanation why. I'll leave you to read that. I won't go through it all, but it's to do with the chemistry of the cells, and there's a lot of literature about this on the internet. As Richard just mentioned, overcharging is not only an issue for lithium-ion. You can damage pretty much any battery by overcharging it, particularly lead and nickel-based batteries. So it's never a good idea. In other words, the products that we are presenting today can also be used in other battery charging applications, not only lithium-ion. And how can the precision of these charging circuits be improved? Obviously, one solution is to use BPGs, that's our ultra-precision bulk metal foil resistors, which provide extremely stable and precise measurements of both the current and the voltage of the cell being charged.
Yeah, the VPG foil resistor is very, very important. It's not just for overcharging, but there's also a very, very big downside to being overly conservative and undercharging these batteries. And again, if we follow along, we'll see that in the remainder of the webinar. Okay.
Thanks, Richard. A few points now about safety, and as we've already mentioned, this is a very important issue with regard to particularly lithium-ion, but also other battery technologies. And excuse me, in order to prevent hazardous situations, most, if not all, lithium-ion battery packs include a small circuit board known as the safety board, which monitors the charge and discharge and other conditions of the battery in order to ensure safe operation. The sort of things that are monitored by the battery board or the safety board include reverse polarity, ambient temperature, so you don't want to be charging a lithium-ion cell below 0 degrees or above 45 degrees. The charge current, to make sure it's not too high. The discharge current, to make sure there isn't a short circuit outside the battery. The charge voltage, if, again, as we mentioned, if the voltage is too high, you wouldn't want that to go to the actual cell itself. And stop charging above 4.3 volts, as we already mentioned. And also to stop over discharge. With lithium-ion batteries, if you discharge them too heavily, around about 2.3 volts, which varies by manufacturer, you will permanently damage the cell and reduce its capacity. So what we can say here is that not only are we talking about battery charging equipment, we're also talking about the safety boards that go inside cells, and VPG's ultra bulk metal foil resistors provide many performance advantages for both the safety board and for the charging equipment.
Just to quickly add, one cannot be too cautious when you're using these batteries, because once the runaway starts, it's going to be a catastrophe for sure, and we will see that in one of the videos.
Okay, this slide focuses on the effects of undercharging. So obviously, one possibility is the effects of the charging voltage. And here we can see that as little as 100 millivolts of undercharging actually results in 10% in reduced capacity. So here we see that the voltage on the x-axis goes from 4.1 to 4.2 volts. This is the charge voltage during the constant voltage phase. And we can see the capacity. So if we're not charging at exactly 4.2 volts, if we're charging at 4.1 instead, we're going to only achieve 90% of our cell capacity. So really, small changes in charge voltage make a dramatic difference in the capacity achieved. Sorry, Richard.
No, it's okay. It's, again, we just see how critical the charging voltage and mode is for the ultimate performance of these batteries, and how critical the sense resistor is going to be in this circuit.
Okay, we have already mentioned this, but just to re-emphasize, the flip side of that coin is overcharging. So what we can say is that our constant voltage phase, the final charge voltage, we need to maintain that within 50 millivolts of the target voltage, which is 4.2 volts. If we allow that to go up, certainly if we allow it to go up to 4.3 volts or above, we are in the very dangerous territory, and we will operate the safety protection devices inside the battery, and we may cause the battery to fail if it's not properly protected. And this could result in venting of harmful gases, a fire, and even an explosion.
Yes, and we're going to witness this in the upcoming video. Kevin, what screen are you on? Sorry.
At the moment, it's failure modes of lithium-ion batteries. Slide number 7, I think.
Okay, thank you. Thank you.
Okay, on this slide, we see a typical circuit diagram for a battery, lithium-ion battery protection schematic. This would typically be on the safety board that goes inside the battery. And what we see here is that there are 3 critical resistors in this circuit, which are required for the correct operation. First of all, we have the current sense resistor. This is in the line, this is our sense, and this is in the line between the charger and the battery. And we're using the voltage across this resistor to detect the current flowing to the battery. So obviously, the precision, the stability, and the accuracy of this resistor directly correlates to the precision and accuracy of our measurement of current. And likewise, we also need to monitor the voltage across the battery. And for this, we normally use, it's typical to use a resistor, 2 resistors in a divider network. And again, the ratio, the stability, the tracking, and the precision of these resistors is critical to the accuracy of that voltage measurement. And this is where Vishay foil resistors bring an important advantage to this application.
Yes, just to very, very quickly add, stability of these resistors is crucial to the performance and the safety of this circuit. Okay,
so we've talked quite a lot about lithium-ion batteries and not too much about resistors up to now. So now we're going to move to talk about resistors and what factors affect the performance of resistors. How can resistors change and what causes them to change in the real world? The main parameters are listed here. First of all, the temperature coefficient of resistance, which is the change in resistance due to changes purely in ambient temperature. And this would apply even to a resistor not on a circuit board, just sitting on the bench or in some equipment, and the ambient temperature is changing. And that is the TCR, and it's normally expressed in ppm per degree C of temperature change. In addition, if the resistor is in a circuit and is powered up and has, obviously in the case of a current sense resistor, may have a lot of power inside it, There's something called the power coefficient of resistance, which is, if you like, the self-heating, and it's changes in the resistance due to the heating effect, the Joule effect, due to the power in the resistor. So these are two discrete, separate factors. One depends on the ambient, one depends on the actual power in the resistor. And these are reversible. So if you take away the temperature change, you take away the power, the resistor should return to its original value. In addition, there are effects which have other effects on the resistor, one of which is a permanent shift due to the soldering process, one of which could be humidity, and one of which is load life, which is how does the product, the resistor, change over time, talking perhaps months, even years into the future. And some other important factors to consider are thermal EMF, which we will come on to, ESD, and also thermal stabilization.
To quickly add, in the upcoming videos, we'll see that TCR and thermal EMF effects are the most critical specs for these current sense resistor applications.
Okay, just looking at the first of those two effects in a little bit more detail, that's the TCR and PCR. So real-life resistors all exhibit these two effects, which are reversible. And once again, the TCR is due to ambient changes in ambient temperature and is expressed in ppm per degree C, and power coefficient is expressed in ppm per watt. Now, what we can say for sure is that for precision current sensing applications, resistors with low, very low, in fact, TC and PCR are required in order to minimize these effects. So if you're going to choose a resistor for, let's say, current sensing in a battery charging application, and that's going into an environment where there is a change in temperature, maybe in a military or space application, and there's also going to be a change in power in the device, then you would want to minimize the effect of TCR and PCR by choosing components with very low characteristics, which is where Vishay foil resistors really offer a big advantage compared to other resistor technologies.
And just interestingly, sometimes power can actually cause an irreversible shift in a very, very poorly designed metal strip type current sense resistor, even though it's within rated power and in a very, very short period of time. Just a little sidebar, interesting application. Okay.
So we just looked at the short-term reversible effects, the TCR and PCR. The other very important effect, having effect on the change in resistance of any resistor, is its long-term stability, otherwise known as long-term drift. And this affects, as I said, all resistors, and it's an irreversible change. It's basically the aging of the part in the application. However, this may not be, in most cases, is not desirable, because you would like to know that if you choose a resistor of a certain value today, then you would like it still to be the same value in several years' time, especially if you have to guarantee the reliability and long-term performance of your equipment. So in this respect, Vishay foil resistors offer an extremely low long-term drift, extremely good, in other words, long-term stability, and it's the nature of the resistor, the material, and the construction and the processing that we do during the manufacturing, and we can actually guarantee the long-term drift and long-term stability of our resistors, and we'll come on to that in a little bit more detail shortly.
To quickly add, foil is the very, very best technology because it's an elastic, homogeneous material that actually gets better and more stable over time. Okay,
so we put this foil in because this slide in because it kind of sums up all of these effects quite nicely in a graphical form. And what we're really talking about with all of these potential changes in resistance is how they all combine to produce the end-of-life tolerance, or otherwise sometimes known as the total error budget. So it's quite common for engineers to look at either the whole system or individual components and say, well, look, I've got an allowance here for the maximum tolerance of this equipment over its lifetime in operation, and therefore it breaks down that the maximum end-of-life tolerance for the resistor, say, is 1%. And knowing all these factors, we can then work, if you like, work backwards, or we can work forwards. If you tell us what the tolerance you require, we can work out for a particular resistor what all of these characteristics are, and will it fit into your end-of-life tolerance requirement. So the factors that affect that are the initial purchase tolerance, the shift due to assembly, which is soldering, any shift due to storage, if it's on the shelf maybe for a long time, any shift due to moisture, if it's in a high moisture environment, the TCR, the load life, the long-term stability, and all of these things add up to the end-of-life tolerance. So it's quite a convenient way, I think, to look at the whole story of resistor stability.
Yes, end-of-life tolerance may be foil's strongest trait. It's as good in 6 weeks, 6 months, 6 years, or 26 years as the day it is installed.
Right, we're nearly through with the characteristics. There's just one or two more to mention, both of which are very important. The first one is the thermal EMF, and this is simply the thermocouple or the Seebeck effect, and it's caused by a difference in temperature across the resistor. So if one side of the resistor on the circuit board in the application happens to be maybe a few degrees warmer than the other side, it's possible for the resistor itself to generate a voltage known as the thermal EMF. And this is clearly not a good thing, because if you have that situation, and if the resistor you're using has a very high thermal EMF, it leads to considerable error on the voltage that you're trying to measure, because this is a voltage it's an unwanted DC offset voltage error, which is sitting on top of the voltage due to the current that you're trying to measure. And if you're not aware of it, you will perceive that the voltage you're measuring is entirely due to current, which it may well not be. So this is very relevant when we talk about low-value current sense resistors, because we're measuring relatively small voltages, and this then becomes quite significant.
Just to briefly add, this can have a tremendous influence on precision low-level current sense measurements, and we will see this in one of the videos. Okay,
and I think this is the last one of the characteristics we wanted to mention today, which is ESD, and its well-known effect to everyone, and it's well known that electronic components are susceptible, but not everyone realizes that resistors too are susceptible, depending on their construction. What we can say is that thick film and thin film resistors are actually highly susceptible to ESD at relatively low levels, around 3 kilovolts. And ESD damage can occur obviously during assembly, but also latent damage can occur in the application, maybe due to lightning or other effects. And what we would like to have is a resistor that is not subject to this damage. And with our Vishay 4 resistors, we rate them at 25 kV ESD immunity, which means that they're not damaged by typical ESD events, unlike thick film and thin film resistors.
Yes, ESD is a bigger problem for thin film than thick film resistors, but it is absolutely no problem at all for foil.
And just to categorize the potential ESD problems in 3 main areas, we can talk about parametric failure. So when we have an ESD event and it will cause one or more of the parameters of the resistor we're using to change, so maybe the resistance value is going to change. The catastrophic damage, obviously the part could actually be totally damaged and fail to work completely. Or latent damage, which probably is the worst one of all, is where there's maybe a small change in the parameters of the resistor every time it gets an ESD event. And this may take many years to happen, but eventually the resistor will go out of either its tolerance or its other parameters of specification and lead to a failure of the equipment. And it's often very hard to diagnose why this has happened, and it's not always suspected that the resistor may well be the cause of this issue. So a resistor that's immune to ESD up to a very high level, such as the foil resistor, will alleviate this problem and increase, therefore, potentially the long-term reliability of equipment in the field.
Absolutely. Latent damage is the most common and the most insidious. Resistors that have been damaged by ESD can appear to operate properly, only to fail prematurely somewhere before their predicted life cycle.
Okay, and now we would like to show you a video about lithium-ion and using Vishay foil resistors for current sensing.
Hi, my name is Rich Zurett. I'm a Senior Development Engineer at the Vishay Precision Group. And this is an overcharged lithium-ion battery that's on the verge of rupturing and catching fire. A disaster in the making. All batteries are potentially dangerous when charging or discharging, but lithium-ion batteries are especially so. Lithium-ion battery charging levels have a tolerance of plus or minus 1%. 1% under results in reduced capacity at 10%. 1% over puts them in the danger zone like this one. At the heart of all battery charging and monitoring circuits is a current sense resistor. Ultimately, the performance of the circuit lives and dies on the performance of the current sense resistor used to sense the current flow to and from the battery. In severe and harsh environments, the performance of the current sense resistor is even more critical because of TCR, power coefficient, and thermal EMF effects. Allow me to demonstrate how Vishay foil current sense resistors are superior to all other technologies and can help avoid a catastrophe like the one we're about to witness. Here is an ultra-precise resistance bridge and test setup that I use to measure and monitor the stability of various types of current sense resistors. These are 50 milliohm 1625 current sense resistors that I have mounted and wired for a terminal. One unit is a thin film current sense resistor, another is a metal strip type current sense resistor, and another is a Vishay foil VCS 1625Z unit. Let's test them one at a time and watch what happens. First, the thin film unit. As you can see, this unit is very sensitive to the effects of hot and cold and not very stable. Second, the metal band unit. Wow! This unit's even worse. The combined effects of poor TCR and bad thermal EMF characteristics could easily put the lithium-ion battery it will be used to monitor in the danger zone. Finally, the Vishay foil unit. Like a rock. Very stable. Definitely my choice for a lithium-ion battery charging circuit. For more information about the complete line of Vishay foil resistors, visit the Vishay foil website. We also offer on-site technical seminars and demonstrations performed by our field design engineers. When working with lithium-ion batteries for high-grade applications, especially where lives are at stake or battery packs are used in remote or inaccessible locations, there is no room for error. The main design challenge in lithium-ion charging circuits is to find that optimal point between overcharging, resulting in catastrophic failure, and undercharging, resulting in reduced capacity. Bulk metal foil resistors are the only choice for achieving that delicate balance.
Okay, there we are. We hope you found that interesting. It certainly was a very dramatic demonstration of the potential hazards associated with lithium-ion battery overcharging. As Richard mentioned at the end of the video, we have quite a few very interesting demo videos on our website, and these demonstrate the different parameters of foil resistors, normally in comparison to other resistor technologies such as thick film and thin film, but not only. And they are available on our website for you to watch at any time, and they highlight, as I said, many of the characteristics we've already mentioned, including the thermal EMF, TCR and PCR, and other effects.
Just to add quickly, yes, we do have various videos. They all show the advantages of Vishay foil. Some are even entertaining, and I recommend all of them strongly.
Okay, so now we're going to look very briefly at the actual technology that we use to manufacture our resistors and how that makes them different to other technologies. So our key technology is that our bulk metal foil resistors are based on a special concept where a proprietary bulk metal cold rolled foil is cemented to a ceramic substrate. So if we look on the right hand side of this diagram, we see that the resistive element that we use is made from nickel chromium foil, and this nickel chromium foil is rolled from an ingot of nickel chromium, obviously, into a foil. And now if we look on the left hand side, we take that nickel chromium foil, which is the resistive element that we use, and we bond it to a ceramic substrate. And this gives us the temperature stabilization because of this mechanical system, which automatically compensates for changes in temperature and gives us a very, very low temperature coefficient of resistance, much lower than other technologies.
Again, the key feature here of the foil technology is its elasticity and the fact that it's a homogeneous material. That is very, very important.
Okay, if we look at the next step, on the left-hand side here, we are looking at top-down on one of our resistor elements. And once we've bonded the foil to the substrate, we then photo etch it, and we produce the resistive pattern, which you can see. The two large white pads are the contact pads. And on the right-hand side, you see these small tabs, which we use for trimming. These are the trimming tabs. And in the expanded view, we can see the before and after trimming view. So with the trimming tabs in place, when the element is manufactured, the current is able to take a shortcut for part of the element and miss out some additional elements. Once we cut one of the trimming tabs, the current is then forced to take some extra part of the resistive element and thereby increases in resistance. And these tabs bring in reducing amounts of resistance, so we trim up to the value you requested, and we are able to trim to 50 ppm with the last tab, so we can offer tolerances of 100 ppm on our resistors. And in addition, this means that we can offer any desired resistance value and tolerance to 100 ppm. You're not limited, with Vishay foil resistors, you are not limited to standard values like 1K, 4K, 7. You can have those if you want. A lot of our customers do have them, but if you want 4K, 2, 3, 7, 5, that's no problem. In fact, you can have any 6-digit value within the resistance range of a resistor, and it adds no cost or delay in the manufacturing process because we trim each resistor we manufacture individually anyway. So it's the same amount of work to make a 1K as a 1.1257K. So this is also a unique advantage of our products.
Yes, unique and complex values of any quantity are our specialty.
Yes, there's also no, as Richard mentioned there, there's no minimum order quantity because if you want one resistor, we simply take one resistor, trim it, and ship it to you. Okay, so looking at summarizing some of the inherent advantages and characteristics of our foil resistors. As I mentioned, we're not restricted to standard values. You can have any 6-digit value within the resistance range specified on the data sheet at no extra cost or delivery time. We're rated on ESD up to 25 kV. And some of the other characteristics we haven't mentioned up to now, but they kind of come along with the technology as additional benefits, are very fast rise time, very fast thermal stabilization, less than 1 second, extremely low inductance, in fact practically non-inductive and non-capacitive design due to the design of the layout and the materials used. Extremely low voltage coefficient, extremely low noise, and extremely low thermal EMF. So all very useful advantages to our technology.
Yeah, I strongly suggest checking the data sheets, or better yet, just go to the video page and you can actually watch these characteristics in action. Okay, and if we summarize, which is difficult to do on one table, but picking some of the main characteristics and looking at how bulk metal foil resistors, that's our resistors, compared to other resistor technologies, we see that for temperature coefficient of resistance, we are much lower. We have much better TC than other technologies. The initial tolerance is also better. Our end-of-life tolerance is much better. We've already mentioned that. Load life stability is much better also. ESD is on a very high level, on the same level as wire wound, but much better than thick film and thin film. Our thermal stabilization is much better, and our noise is much better. So these really are, let's say, as close as you can get really to the ideal resistor. Yeah, just more data, but again, I'll suggest the videos so you can actually see some of this testing as it takes place. Okay, and now the second of our two videos, this time highlighting the advantages of using foil resistors in a solar panel DC to DC converter application.
Hello, my name is Richard Zurat. I'm a Senior Development Engineer at the Vishay Precision Group. I have a short demonstration that shows how VPG VCS Next Generation Z-Foil Current Sense resistors can help with a subject that concerns everyone: energy efficiency and conservation. One of the most important aspects of designing and using any energy efficient electrical device is accurately and consistently measuring the current flow produced or consumed by the device. VPG VCS Next Generation Z-Foil Current Sense resistors, because of their superior TCR, thermal EMF, ESD, and load life characteristics, have a clear advantage over current sense resistors of all other technologies when making current sense measurements. Let me show you just what I mean. I have a scaled down model of a typical solar cell energy system. I'm going to use same size 50 milliohm current sense resistors of different technologies to monitor the charging current provided by the solar cell to the battery under varying ambient temperatures. A very real concern and problem when designing or using an alternative energy source like a solar cell in various real-world environments. First, let me turn on the sun. I'm now going to use a thick film current sense resistor to monitor the charging current to the battery, which I'm going to plot on the laptop. With this light source in this environment, the solar cell output is 50 milliamps. However, what if a similar circuit is to be used in the desert or at a high elevation or any place else where the sun is shining but the daytime air temperature is going to change? Let's see. It's starting off stable and accurately enough, but let me increase the ambient temperature of the thick film resistor a few degrees with this heat gun. It's not very stable or accurate now. I really have no idea what the charging current of my solar cell system is once the ambient temperature changes. Let's do the exact same test with a popular metal band current sense resistor. Wow, this one is even worse. Now the VPG VCS Next Generation Z-Foil Current Sense unit. No change. Stable and accurate regardless of the environment. nor will it change due to self-heating when carrying increased current loads. For alternative energy equipment in remote locations, it can be very expensive to access, repair, and calibrate systems. Therefore, applications such as power supplies, calibration units, and power monitors and wind and solar energy equipment require component technologies that have unquestioned accuracy, stability, and reliability to minimize cost and improve efficiency. For more information about the complete line of VPG current sense resistors, go to the technical library on our website. We also offer on-site technical seminars and demonstrations performed by our field design engineers. As shown, Vishay Precision Group VCS Next Generation Z-Foil current sense resistors must be the preferred choice for these applications.
Excellent. In addition to the videos that we've shown you two of, that we've already mentioned, there are many technical applications on our website, and here I've highlighted two of interest to this webinar. First of all, a document that details 10 case studies where customers of ours have used our products in lithium-ion applications, and this shows briefly how they've used them and the advantages that they have achieved and gained by using our products. This is not only for battery charging, but also battery monitoring and safety applications. And you can see the link to the document there. In addition, we have a similar document for alternative energy applications, which highlights, again, several case studies of customers who have used our products in alternative energy applications, and the reasons why they've used them and the performance advantages that they've obtained by doing so. In addition, we have many other case studies specifically written by individual customers on very detailed applications across a wide variety of applications, showing how they've used our products and talking in detail about the results that they've achieved. So I recommend you have a look at the publication section of our website, and you'll find many interesting documents there.
Yeah, absolutely. Our website is an excellent source for this sort of information.
Okay, so we've talked about the specifications of foil resistors and how they're made, and now we'd like to highlight just a few of the products we have, the ones that really are particularly relevant to this application, more particularly on the power current sensing side. So these are power current sense resistors, and we're just going to quickly highlight the key features of these products, and obviously you can look at them at your leisure in the future. So first of all, we have the surface mount products, starting with our VCS 1610Z. This is a small surface mount power current sense resistor. As you can see from the diagram, it actually has 4 terminals, so it's a 4-terminal Kelvin connected resistor, and it's available with a very low TCR. It has a very low TCR, down to 0.2 ppm nominal, over a wide temperature range, 55 to plus 125. It's available resistance range 0.3 to 10 ohms. The load life is extremely good. It's only has a 0.2% shift with constant operation. That's at rated power, at full power, at 70 C for 2,000 hours. The power rating is actually 0.25 watts, and it can also withstand extremely well the short-term overload.
Yeah, these are very high performance units, very ultra precision. Excellent units.
Following on from the 1610 is the 1625, which is a slightly larger and higher power version. So you can see here that we have a similar resistance range, 0.3 ohms to 10 ohms, similar stability in TCR, except that the power rating is now 0.5 watts at 70 degrees C.
Yes, the TCR on these units is probably not quite as good, but they're still very popular.
Okay, next up we have our CSM family, which incorporates 2 main products, the CSM 2512 and 3637. And if we summarize the parameters of these 2 products, we have TC of 15 ppm per degree C, so slightly higher on the TC side. But what we have is here the very low resistance range of 1 milliohm to 200 milliohms, which is really ideal for many of the higher power, higher current measuring applications. In this case, we can run these parts up to 54 amps and a maximum power of 3 watts for relatively small surface mount components, which is absolutely ideal for many applications these days. And they also have extremely low thermal EMF. And again, they come with all of the other advantages in terms of any value, etc., that we've already mentioned.
Yeah, these are probably our most popular current sense resistors.
Moving on to the leaded products that we have. First of all, we'd like to mention the VPR221Z. As you can see, it's in a TO220 style case, but it's 4 leads. So the inner 2 leads are for voltage measurement, Kelvin voltage connection. The TCR again is very low at 0.2 ppm. Excellent load life. This product is available to EEE and MIL PRF specs for space and military application. It's got extremely low tolerance down to 0.01%, and it covers a wide resistance range, as you can see, and it's able to operate up to 8 watts on a heatsink.
This is a mature product. It's an excellent unit, and I like to use these a lot in my designs.
Okay. Going up now in power, we come to the VFP3 and 4 products. These are rated up to 10 watts on a heatsink. Again, low TC of 2 ppm nominal, extremely good load life, extremely tight tolerance, and resistance range in this case is 50 milliohms right up to 80K.
Yeah, terrific value range on these units.
Here is a product which has extremely low TC, the VCS 331Z and 332Z. These are leaded components. They can be mounted on a heatsink, in which case they can run up to 10 watts on a heatsink. The resistance range is 0.25 ohms to 500 ohms and available with a very tight tolerance of 0.01%.
Yeah, these have an excellent ambient temperature range stability.
Yeah, as you can see, if your equipment is, so let's say, for example, in the range 0 to 60 degrees, you can actually achieve a TC as low as 0.05 ppm per degree C. And these resistors are used in very demanding applications such as medical and X-ray type equipment, as well as lithium-ion battery charging. And finally, really for the products, as I said, this is quite a brief overview. We didn't want to load you down with too much product information, but really this is the best resistor that we offer in terms of performance for this application. We call it CSNG. It's our new generation of power current sense resistors. And we really have developed a brand new technology to produce these products. And these are suitable for the higher power applications. So we're talking about 10 watts in free air, up to 50 watts on a heatsink, and currents up to 20 milliamps, 22 amps, and even higher for values less than 10 milliohms. And as you can see, we can go even from 0.5 milliohms up to 500 ohms with also extremely low thermal resistance. So for the higher power applications where you need that stability and precision, we can offer you a new generation current sense resistor.
Yeah, one of our newer products, and actually it's going to be the subject of one of my videos here very shortly. So
the message there is really whatever the power, from quarter watt up to 50 watts, and even higher with alternative product ranges. We have a broad range of products to offer to meet all potential applications. One quick note of caution, it is extremely important these days to be sure that you are using genuine products because there are many counterfeits in the market purporting to be something that they're not. We know from experience that it would be extremely difficult, in fact impossible, for someone to reproduce exactly the specification and parameters of our full resistors because of the years of experience and knowledge that we have of making them. So it's, again, very important to make sure that you only purchase our products from authorized distributors, all of whom can be found on our website.
I'd just like to toss this in here real quick. Vishay Foil has been around for 50-plus years. I've actually worked for them for 40 of these, helping to refine and perfect this technology. It is the best resistor in the world, bar none. There are no substitutes. Nothing else comes close. Please don't settle for anything less.
Okay, so we're going to hit the last 2 or 3 slides now, and then we'll take any questions. So thank you for your attention. This slide highlights the fact that we have an active policy of not making parts obsolete. In fact, we don't have any obsolete products. We started manufacturing our foil resistors in 1962 with the original, what we call classic foil or C foil, and we still manufacture C foil today in many of our products. And so we can be used in applications where you need to guarantee the long-term availability of your product, whether it's for spares and repairs or for maintenance of equipment for even 10, 20, 30 years into the future. You can be confident that if you use a Vishay foil resistor, it will be available for many years to come.
And just very, very quickly, all of our various products all use Vishay bulk metal foil and share the same high level of performance and quality.
Okay. Our applications engineering support is extremely important to us, and it's extremely important also to our customers. We have a group of applications engineers, of which Richard is one, and our applications engineers are able to take customers' requirements, understand customers' applications, look at circuit diagrams if necessary, but most of all, understand what parameters are important to a customer, and if necessary, take one of our standard products and adjust or extend or improve some of the characteristics, if not all of the characteristics, in order to suit the customer's requirements. And examples of the parameters that we can modify or enhance are the TCR, the resistance value, etc. You can see them all there on the screen. So please, probably 40, if not more, % of all the products we sell have been developed or designed or specified or created by our applications engineering division. So please contact us with your requirements, give us as much information about the application, the power, the ambient temperature, and all these things, and we will offer you the best product for your application. If it's a standard product, that's absolutely fine, but if you need something more, we have the ability, the flexibility, and above all, the willingness to do special products or customize our standard products, should I say, to your application to find the best performing product for your application. And the easiest way to contact us is through our centralized contact line, which is foil@vpgsensors.com.
Yes, we have an excellent engineering group, and to add that all of this additional testing and post-manufacturing conditioning is available for almost all of our products, actually all of our products.
Okay, so thank you. We've now come to the end of the webinar. Thank you very much for your attention.
Yes, thank you.
We hope you found it useful and interesting. And now we'd like to take any questions.
Thank you very much, Kevin. The first question is from Alexandra Alameda. He says he wants to know what the typical temperature coefficient of the foil resistors is.
We have 3 foil technologies which we've developed over the years. The original was called the C foil, the classic foil, and the typical TCR of that is 2 ppm. That's typical. Then we have the K foil, which is 1 ppm per degree C, and most recently, since 2005, we have the Z foil, which is 0.2 ppm per degree C typical, and the maximum for Z foil is 2 ppm per degree C over the range -125 to -55 to +125. So Z foil is our best, but we actually have 3 different foil technologies, but all of them are below 5 ppm. And generally speaking, no other resistor technologies can really come below 5 ppm, certainly not below 2 ppm in terms of TC.
Okay, the next question we have is from Steve Dodds. Does the power rating assume a certain amount of copper on the PCB footprint?
I would say it's just probably it assumes at least the typical amount of mounting copper that would require to hold a component. No additional, not like a large heatsink area. No.
Okay, thank you for that. We're at the top of the hour, so I'd like to conclude this webinar by thanking Kevin Smith, Richard Zurett, and Victor Chertakowski for this fascinating webinar on 4 resistors. Please stay tuned for future webinars with Vishay Precision Group and Element 14. And with that, I'd like to thank our presenters and our audience and say goodbye. Goodbye.